Cool. All right. Well, welcome back, everybody, to another exciting session on CE 397, Control Theory for Smart Infrastructure. So let's quickly just recap what we covered last time. So last time I introduced you to a concept that you had never seen or conceived of before, and that was matrix functions. So we showed how we could apply arbitrary analytic functions to matrices. We showed how these functions were defined in terms of their Taylor series expansion. So just as we can define the Taylor series of a scalar function, we can also define the Taylor series of a matrix function as well in terms of this infinite sum. And we also showed how a matrix function applied to some arbitrary matrix A is equivalent to applying that function to the matrix's eigenvalues. So that provides a convenient way of computing an arbitrary function of a matrix. Could be, the sine of a matrix, the cosine of a matrix. It could be, here's another good one, the inverse of a matrix, right? So let's say our function is, P of A is equal to A inverse, or 1 over A, right? So this would be equal to V times lambda inverse times V inverse, right? So this also shows us another reason why we can't take the inverse of a matrix that is not full rank. Why is that? What happens if we try to take the inverse of this matrix here if our matrix A is not full rank? So if a matrix is not invertible, what does that imply about the eigenvalues of that matrix? There's at least one eigenvalue that is equal to 0. So what happens when we try to apply this function? We will end up with 1 over lambda 1, 1 over lambda 2, all the way to 1 over lambda n. If any of those lambdas are equal to 0, and then times V inverse. If any of those lambdas are equal to 0, what happens when we try to take 1 over 0? It's not undefined. So this shows another reason why we can't take the inverse of a matrix that is not full rank. Okay, so in summary, functions of a matrix can be expressed as functions applied to the eigenvalues of that matrix. Okay, and we took this concept and we showed how we could apply it to solve LTI systems of ordinary linear differential equations. We showed the general form of the solution for LTI systems. In brief, it was almost exactly the same as the solution for a scalar LTI system, except in this case, our solution x of t is a vector, our initial condition x naught is a vector, our inputs from time 0 to time t are also vectors, and A and B are matrices, right? So it's essentially a matrix version of the solution, complete solution to a LTI system. And we specifically looked at different ways we could compute this term here, which was important for solving this equation, the matrix exponential. And we showed 2 different methods that we could use to solve that matrix exponential in practice, one via the eigendecomposition and one via the Laplace transform. And we went through a couple examples of computing the matrix exponential for an example system. Okay, are there any questions on these concepts before I move on to the subject of today's lecture? Any questions on solutions to multivariable LTI systems? All right, well, let's go ahead and move forward. So towards the end of class, as I mentioned, we're going to be talking about applying control to multivariable systems of differential equations. So whereas in the first part of the course, we looked at single variable systems, towards the end of the course, we're going to be looking at control of multivariable systems. And we're also going to be looking at the problem of state estimation, in which we are trying to observe the internal hidden states of a multivariable system from some set of observed outputs. But this raises the question, so first, before we can attempt to control a system, we need to know whether or not it's possible to control that system, okay? And that brings us to the concept of controllability. Similarly, we need to know, if we are trying to observe the internal states of a system, if it's possible to reconstruct all of those hidden internal states from our limited set of sensor outputs. And that arises in the problem of observability. So in summary, before we can control and estimate our LTI systems, we need to know whether it's possible to do so. And we will figure that out through these dual concepts of controllability and observability, which I'll introduce today. Okay, so in particular, we're interested in two interrelated questions. So for controllability, we're interested in, do we have the ability to steer the state of the system to any desired state using some set of inputs? Okay, so do we have the ability to steer the state xt to some desired final state using a set of inputs, which I'll just write as UT. So can we drive the system from some arbitrary initial condition to any desired final state that we want in some finite amount of time? And in terms of observability, we're interested in the following question. Can we infer the internal state? So can we infer the state x of t exactly, given that we know a time history of outputs y and a time history of inputs ut? So these are the fundamental questions we are interested in when we're talking about controllability and observability in the abstract. Let me give you a couple examples of controllability and observability questions we might be asking in reference to civil engineering systems. So you may remember from homework 5, there was a problem on a 3-story structure, right? So we had a structure, it had 3 different stories. Okay, and let's say we have the structure and we have an actuator placed on just one of the floors. And this actuator is capable of inducing some control force F of t. So a question we might be interested in with reference to controllability is, can a single actuator placed on the first floor independently control the position and velocity of all 3 floors independently? So that would be a fundamental question that we're interested in terms of controllability. Can a single actuator independently control x and x dot are 2 states for all floors independently? Who thinks that this is possible? Who thinks this is not possible? Okay, so we got 2 votes for impossible. Okay, how many votes for possible? None. Okay, so got some holdouts here. Okay, so that would be a question that we're interested in terms of controllability. We're actually going to examine this towards the end of the lecture today, whether this is possible or not. Another question we might be interested in is the observability question. So let's say we have a sensor placed up here on the second floor. So another question we might be interested in is if we have just a single sensor placed on the second floor that's measuring the displacement, is it possible to reconstruct the displacement and velocity of all three floors? So given a single sensor, is it possible to reconstruct the position and velocity of all three floors? In other words, you have outputs, which are simply the displacement at the second floor. You have a dynamical model of the system, which you know to be true. And you know the inputs to the system. Is it possible to reconstruct and infer these states at the unobserved locations? Okay, who thinks that this is possible? Got one vote for yes. Who think this is not possible? So I got one vote this time. Okay. So we'll be looking at this problem as well. Let's see that Kelsey is the bravest in advancing an answer. So thank you, Kelsey. We'll be looking at this problem as well towards the end of class. Okay. But these are some of the fundamental questions we're interested in with respect to controllability and observability. Let's give another example that may be familiar to other students, perhaps in the water resources domain. So let's say we have a network of reservoirs. We have a network of reservoirs. Each one of them has some water in it. And these reservoirs empty into each other. So this reservoir empties to this reservoir empties to this reservoir empties to this reservoir. They all have some water in them. And maybe this reservoir empties out here. So one question we might have is, if we have a valve placed on this branch up here that can control the flow of water on this branch, is it possible to independently control the water level in all of the reservoirs? Who thinks that it's possible? Okay, who thinks that it is not possible? Right. So this one might be a bit more intuitive, right? So if you only have a single valve located on this one branch, is it possible to control the water level in this reservoir? No. Right. So this one, we may have a little bit more intuition for what the controllability properties are. You'll see on the homework what conditions are needed for controllability for this particular network. Okay. And similarly, let's say we have just a sensor placed on this downstream reservoir. And it is measuring the water level in this reservoir. Is it possible to infer the water levels in all of the reservoirs just from sensor observations at the most downstream reservoir? So who thinks yes? Who thinks no? And most of you think no, okay? So it turns out that no, it is not possible. But it is possible if there's a sensor on one more reservoir. So if you have a sensor either here or here, and you have a dynamical model of the system that perfectly describes its behavior, it is possible with two sensors, one at the outlet and one at one of these upstream reservoirs, it is possible to exactly infer the internal states, i.e. the water levels, at any point in time. Okay, so that would make the system observable. Okay, are there any questions conceptually on these two examples? All right. One more example. So it doesn't necessarily have to involve a system with multiple parts. Let's say we have a bioreactor. For instance, let's say we have some sort of bioreactor. It's modeled as a continuously stirred tank reactor, and it's got some different constituents in it. And let's say we have different constituents within this bioreactor. We may have some biomass. We may have some substrate. We may have other parameters like the temperature of the tank or the oxygen level. And we may want to know, for instance, is it possible to infer what the biomass concentration is in the tank by observing some subset of other variables? So for instance, if we can only observe the oxygen level, if we can only observe the carbon dioxide level in the tank, or if we can only observe the temperature, is it possible to back out what the biomass concentration in the reactor must have been? So this would be another example of an observability problem. Yeah, and this can be really useful, especially if you are dealing with systems where the internal states are difficult to measure. So things like biomass concentrations often need to be sampled for an accurate measurement. Sometimes it can be useful to try to infer what those states must be through measuring some other variables. Okay. So are there any conceptual questions on controllability or observability before I start moving into some of the more formal material? Any questions conceptually on any of these examples? Can anyone think of another example of a controllability or observability problem in civil engineering? Any other examples? Perhaps something related to your research? Was there someone who said something? No? Well, is anyone doing a course project related to state estimation or observation? Maybe a little bit. Okay. Well, so I think your project is more on parameter estimation, but you can treat parameters as being kind of similar to states in some ways. Okay, cool. Well, with that, I will go ahead and move on. So let's give some formal definitions of controllability and observability. We're going to give a formal definition, and then we're going to kind of intuitively look at the problem of, for the controllability case, determining the input that steers us to a desired final state, and for the observability problem, determining our optimal estimate of a prior state given some series of outputs. Okay, so let's look at the formal definition of controllability. Okay, so this is our formal definition. So we say that a linear system is controllable over the interval. So it's controllable over some interval T naught to TF for our initial time to our final time, if there exists at least one input. So this would be a series of inputs over each time step, which I'll just call U. Let me write this as, it's actually U naught, U at time one, all the way through U at the final time. So it is controllable over this interval if there exists at least one input U, which transfers our state xt from any initial state which I'll write as xt naught to the origin. So I'll write xtf is equal to 0. Okay, so this is the definition of controllability. A linear system is controllable over some time interval if there exists at least one series of inputs which transfers our state from any initial condition in the state space to the origin. Okay. Similarly, we say that the system is reachable if it goes the other way around. So it's reachable if we can go from x t naught is equal to 0 to any desired final state. Okay. And for a linear system, these two definitions are equivalent. So for a linear system, controllability implies reachability. Okay, so let's take a look at the controllability problem in a bit more detail. We'll get to the observability problem a little bit later, but let's just conceptually go over this concept of controllability. So let's say we have some state space. I'll call this x-axis x1, this y-axis x2. And let's just look at reachability now, because it's equivalent to controllability, and it's perhaps a little bit easier to talk about. So for the reachability case, we have our initial x at the origin, our initial state at the origin. So I'll call this x at t naught. And if our system is reachable, then it's possible to go from this initial position to any location in the state space. It's possible to find some input that drives us from the origin to any position in the state space. All right, so there exists some input that will drive us from the origin to any location in the state space. So let's think about how we can go about determining whether this input exists or not. Let's look at the discrete time case first, because it's a bit easier to think about. And let's think about how we can find an input that will take us from the origin to any position in the state space. So we have that our system in discrete time is described by the difference equation x at time k plus 1 is equal to a times xk plus b times uk. And let's say that we have some desired final state. We'll just call it xk. Okay, so it's some desired x at time k. All right, so we can iterate from time 0 and just find how this equation, what comes out if we just iterate from time 0. Okay, so we know that x naught, what is x naught equal to for the reachability case? 0. Okay, so we're starting at the origin, so x naught is equal to 0. Okay, what about x at time 1? What will that be equal to? Right, so it'll just be b uk. Oh, sorry, b u 0, right? So x at time 2 will be equal to, you can fill this out, it'll be equal to a times x at time 1 plus b times u at time 1. And we know this expression for x at time 1, right? So this will be a b u0 plus b u1. Okay. Similarly, x at time 3 will be equal to a times x at time 2 plus b times u at time 2. And if we substitute in our expression for x2, we will get a squared times b times u naught plus ab times u1 plus b u2. Okay, so you can kind of see the pattern. So we can go ahead and take this expression here, and we can express this as a matrix equation. So this is a linear equation. We can take this recurrence relation and express it as a matrix equation. So let's go ahead and do that. We have that x at time k, if we just follow this recurrence relation, will be expressed by the following matrix vector product. So we have a at time k minus 1 times b, a k minus 2 times b, and so on, all the way to ab, b, times the vector of all of our inputs over all time steps. So this will be u naught, u1, sorry, that should be u naught, all the way through uk minus 1. All right, so we can also express this as, we let this entire expression here be some matrix G. Then we can write this matrix vector product simply as xk is equal to G times U, where U is this stacked vector of all of our inputs. Okay, let's go ahead and take a look at the dimensions. So first of all, let's look at each of these terms here. What will each one of these entries be in this matrix? What is the dimension of AB? What is the dimension of AB? Well, I actually haven't given you the dimensions of these different matrices. Let's just say that U naught here, this is of dimension RP. It's in pineapple. Okay, so AB here will be R NP. Oh, sorry, N by P. Okay, so the dimension of U, all of these stacked inputs together, will be equal to what? What is the dimension of this entire U vector here? So it'll be Kp, right? It's going from 0 to k minus 1. So it'll be R P times K. Okay, what will the dimension of G be? So actually, I'll write it down here. U is in R P times K. What is the dimension of G going to be? Kind of by the same logic. I believe that is right. So it will be, yeah, it'll be in R N by P times K. Okay, and in this case, which of these terms is unknown? So we're trying to find the input that takes us to some desired final state. So which of these terms is unknown here? Yeah, U is unknown. Okay, so we have this matrix vector product. U is unknown. Is G going to be a tall matrix or a wide matrix? It's going to be wide. It's going to be quite wide, actually, right? So it's only n rows tall, and it's going to be P times K columns wide. So what type of problem is this? We're trying to find U, and we have that G is wide. Underdetermined, right? So there are many, many different inputs that will drive us to the desired final state if the system is controllable, right? We can find the minimum norm input, however, by computing the right pseudo inverse of G. Okay, so we can take this expression here, and our best estimate, our minimum norm estimate for our input that drives us to that final state will be given by G transpose times GG transpose inverse times our desired final state X of K. Okay, so let's take a look at this term GG transpose. We're going to take this G here, so it'll be A K minus 1, B A K minus 2, B all the way through A, B, B. And we're going to take the product with the transpose of itself. So this will be B transpose, A transpose, K minus 1, right? Because when we take the transpose, we reverse the order all the way through B transpose A and B transpose. So if we take this product and we compute it, so this is similar to just taking the dot product between two vectors, we will get that GG transpose is equal to the following sum. It's the sum from I equals 0 to K minus 1 of A to the ith power times B transpose times A to the ith power transpose. And this sum here has a very special name. This is called the discrete time controllability Gramian. And it turns out that the system is completely controllable if and only if this controllability Gramian is invertible. So note that this controllability Gramian is a matrix. It turns out that the system is controllable. We can drive the system from the origin to any desired final state if and only if this matrix is invertible. Okay, and we can show this if we, there's a formal proof in the notes, which I'm not going to go through because it's very long. But if we go ahead and take this expression and we substitute it back in, so let's say we have that we know that xk is equal to gu. Let's substitute in our expression for u hat, which is our best, our minimum norm estimate of u. We have that xk is equal to gu. And let's just substitute in u hat here. Our u hat we know is given by G transpose times GG transpose inverse times xk. So we have G times G transpose times quantity GG transpose inverse times xk. So if our controllability Gramian is invertible, what happens to this expression? You can also group it like this. So if the controllability Gramian is invertible, right, these cancel out, and we get that we can drive the system to some final state x of k using our minimum norm input u. Okay, so that is the fundamental test of controllability. A linear system is controllable if and only if the controllability Gramian is invertible, where the controllability Gramian for a discrete time system is defined like this. Okay, let me go ahead and write out the cases for both the continuous time and discrete time systems. So we can say that an LTI system is controllable if and only if the controllability Gramian is invertible for full rank. And there's a formal proof for both directions. I will just give you the expression for the controllability gradient for both the continuous time and the discrete time case. So in discrete time, it's just the expression that we gave before. We can write the controllability gradient as GR from time 0 to t is equal to the sum from I equals 0 through k minus 1 of a to the I, b transpose, a to the I transpose. Okay. For continuous time, it looks similar. So in continuous time, it will be, instead of this sum, we'll have an integral from 0 to t of e to the at b transpose e to the a transpose t dt. Okay, so this is the fundamental test for controllability. A system is controllable if and only if the controllability gradient is full rank, where we have that the controllability gradient for a continuous time and discrete time system are defined as follows. Okay, are there any questions on this demonstration? Any questions on this demonstration before we move on? Okay, let's go to observability. This one's perhaps a little bit harder to wrap your head around, but I will take you through it carefully here. Okay, so let's say we have a state space again. It's called the x-axis x1, y-axis x2. Let's say we have some initial condition, which I'll write as x at time 0. We have some final condition, which I'll write as x at tf. And the system, may evolve over time like this. Okay, so the system will evolve from x at time 0 to x at time tf. And let's say that we only have access to the first state variable. So we can only observe x1. So we'll have a series of measurements of the system from time 0 to time tf. And our y's, our observations, will just be x1, so just the first state variable over that entire time period. So this will be y at time 1. This here will be y at time tf. Sorry, this should be t naught, not t1. And we might also have, all these measurements in the interim. This might be y ti, for example. So we have some system that evolves over time. We can only observe one of its state variables. Okay. And we're interested in whether we can, given that series of observations, if we can recover the full state at any previous point in time. In particular, whether we can infer the initial state, because if we can infer the initial state, that means we can infer the state at any other point in time. So actually, before I do this example, no, that's okay. Never mind. I'll just do this example. Okay. Okay. So just as before, we can take a look at the system in discrete time step by step. Okay. And we know that our observed output yk, let's just assume that there's no input to the system. So it's sufficient to just look at the case where there's no input. So we're going to assume no input u. So in other words, x at time k plus 1 is just equal to axk. And yk is going to just be equal to c times xk. All right, so let's just step through step by step again. We have that yk is equal to c times xk. So that means y naught is equal to what? What is our initial observation equal to? based on this equation here. C times X naught. Okay, our Y at time 1. What will this be equal to? C times X at time 1. Okay, and we can re-express that. How can we re-express that in terms of X naught? Yeah, so it'll be C A X naught. Y at time 2 will be equal to C times, it ends up being A squared X naught, and so on and so on. And you will end up with a matrix equation again. Well, actually, we can just equate this as two vectors being equal to each other. So we have Y naught. So Y naught is equal to C X naught. Y1 is equal to CA X naught all the way through, let's just say YK minus 1. YK minus 1 is equal to C times A to the K minus 1 X naught. And that just comes from iterating this recurrence here. Okay, we can express Y at each time step in terms of a series of matrices times X naught. All right. So we can go ahead and expand this out. I'm actually going to move to the next page here. So again, we have Y naught, Y1, all the way through YK minus 1 is equal to, we had C X naught, CA X naught, all the way through CAK minus 1 X naught. And we can just go ahead and factor out X naught. So we have this vector here. Actually, it's not a vector, it's a matrix C, CA, so CA squared, all the way through CAK minus 1. And we could just factor out X naught here. Okay, so let's say that each of these Y's is of dimension Rm. We know that X naught is of dimension Rn. And each of these terms here will be of dimension R m by n. Okay, so what are the dimensions of each of these terms? Let's write out this equation as a matrix equation again. So let's write this out as capital Y is equal to H times X naught. So this here is capital Y. What's the dimension of capital Y? Right, so it'll be R MK. And what is our dimension of this vector here? Sorry, this matrix here. This will be H, which is N. What's our dimension here? So the number of rows of each of these is going to be M, as in Mike. And there's K entries, so that will be M times K by N. Okay, and what's our unknown? What are we trying to solve for here? Yeah, we're trying to solve for X naught. So this here is our unknown. Okay, so we again have this equation of the form of a matrix vector product is equal to a vector. Okay, is our H matrix here tall or wide? Yeah, so in this case, it's going to be tall, which means that the problem is overdetermined. Okay, overdetermined. So we can find our optimal estimate of x naught by applying the left pseudo inverse. Okay, so our optimal estimate of x naught is given by H transpose H inverse times H transpose I. Okay, and if you compute this H transpose H, you will get an expression similar to how we computed GG transpose before. H transpose H will give you the following equation: the sum from I equals 0 to k minus 1 of A to the ith power transpose times C transpose C times A to the ith power. And this expression here is called the observability Gramian. And it turns out you can prove in a similar way that a linear system is observable if and only if this observability Gramian is invertible or full rank. Okay, so this is, again, the fundamental test for observability. If this matrix here is invertible, that means that we can recover the internal state of the system at any previous point in time, given some set of measurements. Okay, and we can verify that just as we did before. So if we have that x hat is equal to H transpose H inverse H transpose Y, we have that Y is equal to H times x naught. So if we simply substitute in this expression for Y, we get that x hat naught is equal to H transpose H inverse times H transpose H x naught. And what happens to these two terms here? So just as before, these cancel out, and we can recover perfectly the internal state of the system at any previous point in time, if and only if the observability Gramian is invertible. Okay, so let me give you the formal expression again. So we'll do it for both continuous and discrete time. So the LTI system is observable if and only if the observability Gramian is full rank. Okay, where the observability Gramian for continuous time and discrete time are expressed as follows. So I'll do discrete time first because we just did it. So we have that GO from time 0 to t is equal to the sum from I equals 0 to k minus 1. Actually, let me write k instead of t. We have A transpose to the ith power times C transpose C times A to the ith power. For continuous time, it's very similar. So the observability Gramian from time 0 to t is equal to E to the A transpose T, C transpose C, E to the A T dt. Right, and those are the fundamental tests for controllability and observability. Note that these tests work for both linear time invariant and linear time varying systems, as long as you put in the appropriate expression for your state transition matrix. So this is really the fundamental test for controllability and observability. However, in practice, it's usually easier to use a different test. There are many different tests. I have several of them in the notes, but probably the most convenient and the one that is most convenient for your homework is what's called the Kalman rank condition. So this is probably the most widely used test for controllability and observability, and we'll be using this for a couple examples in this last part of the class here. So in practice, it's much easier to compute controllability and observability through what's called the Kalman rank condition. So I will give that condition for you now. So let's say we have the following matrices. So we have let A be in our n by n, November by November, B be in our n by p, so November by pineapple, and C be in our m by n, Mike by November. So we say that the pair AB is controllable if the following matrix is full rank. QC, which we call the controllability matrix, is equal to B, AB, A squared B, all the way to A n minus 1 B. It is controllable if this matrix here, sorry, I said full rank, but that's not true, has rank equal to n. So rank equal to the dimension of your state vector, or the dimension of the state transition matrix A. Similarly, the pair AC is observable if the observability matrix, which I will define as QO, and this is equal to C, CA, CA squared, all the way through CA n minus 1, has rank n. Okay, so you can show these conditions using the controllability and observability Gramian respectively. It's a bit too lengthy to show that, so I'm not going to do it in class, but these are derived from those fundamental tests of controllability and observability, defined in terms of the two Gramians. So let's go ahead and use these conditions to solve a couple of problems. We're going to be looking at whether or not some systems are controllable. I'll be going back and revisiting some of the problems from earlier in class to test whether they are controllable and observable, and we'll see which of you were correct. For those of you who volunteered an answer. Okay, so let's take a look at the structural system that we are familiar with. So we have our structural system. It's dynamic expressed in state space form, or x dot t, x double dot t. And my mouse is going all kinds of wild here. So forgive me if I draw a little oddly. Okay, our A matrix is 0, 1, negative k over m, and negative c over m, times xt, x dot of t, plus 0, 1 over m, times f of t, our input force. And let's just say that we can only observe the displacement. So our output x of t is equal to 1, 0 times our state vector xt, x dot of t. Okay, so this here is our A matrix. This here is our B matrix. And this here is our C matrix. Let's test whether the system is controllable. And let's test whether it is observable. Okay, first, for controllability, we need to use, let's use the Kalman rank condition here. So we are going to test whether our controllability matrix is full rank. So in this case, our length of our state vector is 2. So our controllability matrix will look like the following: B, A, B. So let's quickly compute AB here. AB is equal to the matrix A times the vector B, which will be 0, 1, negative k over m, negative c over m, times B is just 0, 1 over m. And if you carry out this multiplication, up in the first row, you will get, what will the first row be? 0 times 0 plus 1 times 1 over m is just 1 over m. In the second row, we will have negative k over n times 0 plus negative c over m times 1 over m will be negative c over m squared. And we know that b is simply equal to 0, 1 over m. So our controllability matrix will be 0, 1 over m. And the second column will be 1 over m, negative c over m squared. So what is the rank of this matrix? 2. Right? You can tell just by looking at it that it has 2 linearly independent columns. So is this system controllable? Yes. This is controllable. So rank is equal to 2. Let's quickly do the observability case because it's pretty quick and easy. We have that our observability matrix is equal to C and CA. So we know that C is just equal to the row vector 1, 0. CA is equal to 1, 0 times our matrix A, which is 0, 1, negative k over m, negative c over m. Okay, and if we carry out this multiplication, we end up with 1, 0, 0, 1. So this will be just, oh, sorry, this is wrong dimension here. So if we carry this out, we will end up with CA equal to 0, 1. Okay, so if we take these and we stack them together, we get that QO, our observability matrix is equal to 1, 0, 0, 1. And we can tell by looking at it that this is definitely a full rank. So our system is observable. Okay, so this is generally the easiest test for controllability and observability. But note that it only works for LTI systems. So if you have a linear time varying system, you cannot use the Kalman rank condition. You'll have to use another test, probably the controllability Gramian test. Okay. All right. Are there any questions before I move on to our next example? So I'm going to move on to some examples that are a little bit more complicated. And for these, we will need to code them. We'll need to do a little bit of coding to determine observability and controllability. So are there any questions on this example or just the general concepts of controllability and observability? I see Kelsey is following along there. Cool. So you don't, these are just examples I'm going to show. You don't need to follow along on your laptop there. But yeah. Are there any questions on this example or the concepts of controllability and observability before I move on? Nope. Okay, well, let's go ahead and take a look at a few more examples. So first, I'm going to take a look at the question that I posed to you at the beginning of the lecture today. Let's say we have a multi-story structural system. Okay. Let's say we have a multi-story structural system and we may have actuators only located at some subset of the floors. Is it possible to completely independently control each of the floors and place their final state wherever we want them to be? So most of you said that no, this was not possible. So with the actuator on one of the floors, that it was not possible to independently control each of the floors. Let's see if that is true. Okay, so I'm going to go ahead and set up my notebook here. I have, using the solutions from homework 5, I've specified a state space equation for our 3-story structural system. Okay, so I have these component matrices. You may remember this from homework 5. These are what each of those stiffness, damping, and mass matrices should look like. And you can kind of block them together in block form like this. So your A matrix will look something like this. Your B matrix will look something like this. And your C matrix, let's say at the beginning that we can just observe the position of all 3 floors. In that case, your C matrix will look like this. So you can independently observe the position or the displacement of each of those 3 floors. Okay, so I'm going to go ahead and just simulate the system first, just to show you that it works. So what I've done here is I've computed the matrix exponential using scipy.linalg.matrix exponential, and I'm just taking that matrix exponential and evaluating it at different points in time, t. Okay, and using this, I can simulate the system. Okay, and if we go ahead and plot out the result, we should see that for an impulsive input, our structure will respond like this. So this is the displacement of each of the floors. I'll play a little animation to make it a bit more clear what's happening. Okay, so this is what our structural system should look like if it's hit by an impulsive input at the first time step. So you'll see that the structure kind of bounces to the side and then it kind of springifies itself back to the center. Okay, so that's what our simulated system looks like. Now let's say that we can place an actuator on each floor. Okay, so we have our initial B matrix, which consists of having an actuator on each floor. That's why you have three ones there. And let's see if the system is controllable with this controller configuration. So how can we do that? So probably the easiest way is to construct that controllability matrix, right? So that in this case would be something of the form, right? So for this case, it'll be something of the form QC is equal to B, AB. It's a dimension 6, so we'll have A squared B, A cubed B, A to the 5th power B. So we need to construct this matrix. We can do this using a loop. So let's go ahead and do that. So what I'm going to do is I'm going to use Python's list comprehension syntax. So I'm going to say np.linalg.matrix power. So this raises a matrix to a power. I say np.linalg.matrix power on A, raised to the ith power times B for I in range n, where n is the length of our state vector, which will be 6. Okay, so carrying out that list comprehension, we got each of those matrices. Now all we have to do is stack them up horizontally. So we can do that using np.columnStack. And this is our controllability matrix, right? So I've just stacked each of those matrix products together. So this I will call QC. And now what can we do to determine whether the system is controllable or not? What does this matrix need? So what rank does this matrix have to have for the system to be controllable? And which is 6, right? So let's go ahead and compute the rank. We can use that the function np.linalg.matrix rank of QC. And we see that the rank is 6. So this system is completely controllable. Let's go ahead now and let's take our initial control input matrix B, and let's just take this matrix and make it so that we only have an actuator on one of the floors. So how can we do that? Yeah, we take one of the columns from this matrix. So let's say we have B hat is equal to B. We'll select all the rows and we'll just select column 0. So our B hat, our new input matrix is the following. Now we can just take that exact same code we wrote before and replace B with B hat. Okay, and let's see whether the system is controllable with just one actuator. First of all, does anyone want to change their bets? Who thinks the system's going to be controllable? Who thinks the system's going to be controllable?
So the definition is if any stateful can reach the origin, right?
So yes, so equivalently, you can drive the system from the origin to any desired final state, which is 6-dimensional, right?
But if it's to the origin, right, and it's an oscillator, then won't it always go to the origin? Even if I just put in an input to 0, so there is always, right? Like even with no actuators, would it not be controllable?
That's a good point. I'll have to think about that. That sounds correct, though. In terms of reachability, though, you also have to have it so that you can drive the system from an initial state at the origin to any desired final state. So stability doesn't necessarily imply that. So let's just do a quick show of hands. Who thinks that's going to be controllable? Who thinks it's not going to be controllable? Okay, so most of you think not controllable. Let's find out. It's controllable.
So can you test if you have inputs of 0, so there is no actuator? Is it still controllable?
If there's no actuator at all, let's. So what we can do is just take this matrix times 0, right? Because now it'll just be all zeros. And the matrix rank is 0. So it is not controllable if you don't have an input. But if you just have a single actuator on one of the floors, and it doesn't matter which floor we choose, it'll still be controllable, meaning that we can drive the system from the origin to any desired final state, with that state being defined in terms of the position and velocity of all 3 floors. Okay. And you can do the same test for observability and show that the system is also completely observable, meaning that if you just measure the displacement at one of the floors, you can recover the position and velocity of all 3 floors using our dynamical model and using the pseudo inverse like I showed you earlier in class. Okay, so that's an interesting finding, but you may be wondering, is it really feasible to control the state of our 3-story structural system using a single actuator? And it turns out that even if it's possible to drive it to some final state, it may be unrealistic to do so given a single control point for that system. So I'm going to quickly show you. Let's take a look at our multi-room heater system. And I want to look at whether it is controllable using heaters in rooms 1 and 4 and heaters in rooms 1 and 2. And I want to look at how the total heating energy input needed to independently control each of the rooms is related to the controller placement. Okay, so first let's evaluate whether the system is controllable with these 2 controller configurations. So I have our heater system. So this also is from homework 5. Is the system controllable with heaters in rooms 1 and 4? So we can do that using a similar technique as we used here. In this case, we have that our B matrix will be equal to just the first column and the 4th column of the identity matrix. Oh. Sorry, that is correct. I think it's because I set I. So let me just restart here. Okay, so let's take a look at our controllability matrix. So in this case, is the system controllable? We have 4 rooms. The rank of our controllability matrix is 3. So it's not controllable with heaters in rooms 1 and 4. So on the diagonals, let's take a look at whether it's controllable with heaters in rooms 1 and 3. And so for this system, it is controllable with heaters in adjacent rooms, but not with heaters in rooms along the diagonal, which is kind of interesting. But more towards my point from earlier, okay, we showed that if you have an under-actuated system, you may be able to completely control the system, i.e. drive it to some desired final state, but getting there might take you through a trajectory that's not feasible in practice. So let's look at what happens when we try to control the system to bring it to a desired final temperature of 30 degrees Celsius in the first room, 10 in the second room, 20 degrees Celsius in the third room, and 5 in the fifth room, using just 2 heaters located in the upper 2 rooms. Let's see if we can do that. So theoretically, we should be able to do that because the system is completely controllable. I've used the minimum norm, computed the minimum norm input using the pseudo inverse shown in the first part of class. And this is what the minimum norm heat inputs needed to drive the system to that final state look like. Let's look at what the actual simulated system looks like when we put in those heat inputs, right? And to drive our system to the final state, it has to first bring the heat in room 1 up to a high point and then bring it back down. And similarly, this room has to first go down and then back up. So it's kind of a convoluted path. And depending, which rooms we put the heater in, you can get paths that look even stranger. Oh, that doesn't look right. Sorry, because that's not, yeah, 0, 1. Right. So in this case, it has to bring the temperature in the room up to 70 degrees Celsius before it can bring it back down to the desired temperature. And this just has to do with driving the system to that desired final state. Using heaters in just 2 of the rooms is not practical in practice. So if we have heaters in all of the rooms, let's make this vector 0, 1, 2, 3. You get a minimum norm heat input that looks a bit more sensible. And the simulated temperatures in your room look a lot more sensible. It just gradually brings them up to their desired final temperatures. Okay, so just to note that just because the system is completely controllable does not mean that the energy, the control energy needed is practical or feasible in the real world. Yes.
So in this example, we saw that the heat input for some of the heaters, it actually is negative. Is there a way to specify or like a test for controllability with constraints on what the input can be if we only have heaters and not cooler?
Right. So the definitions of controllability and observability that I gave you are only for linear systems. So linear systems do not admit constraints on the input because then it would no longer be linear. There are ways that you can look at the controllability and observability for nonlinear systems, but it's much more difficult and there are much greater caveats on whether it's controllable or observable or so on. It's harder to analyze essentially. Yeah. Okay, and with that, I am out of time, but I will be holding office hours today at 4, and remember that I will be extending homework 6 until tomorrow night, so you also have tomorrow to come see me at office hours about that as well. Okay, with that, have a nice day, and I will see you on, well, sometime this